All right, so good afternoon, everyone. Thank you so much for joining us for our Talk Tuesday. We are very pleased to have Dr. Anthony Arendt. He's a Senior Data Science Fellow and the Director of Community Engagement at the University of Washington eScience Institute. His background is Arctic and Alpine glaciology, sea level change, and remote sensing. We are excited to hear his talk titled Open Science Practices in Support of Active Research Applications. Dr. Arendt, welcome. Please, the floor is yours.
Thanks so much, Josephine, and welcome everyone. I really appreciate this invitation to meet with you today. I had an opportunity to visit with the iHARP team up in Alaska this summer, and now I have a chance to share with you a little bit about the work that we're doing in the open source space and how that might apply to your work as Arctic researchers. As Josephine mentioned, I have had a career in Arctic data science, going back to some field work back in the early part of my career, spending a lot of time out on the glaciers, digging snow pits, was really engaged in a lot of data collection on the ground and using aircraft. And then I kind of transitioned into a space where I was a little more focused on modeling and software development. I was engaged in some of the early work around developing global inventories of the Earth's mountain glaciers, the Randolph Glacier Inventory. So we helped to establish that community effort and built this inventory that's now being used for a lot of different applications. And in the later phases of my career, since about 2020, I've been working more in the data science space, really thinking about how do we help scientists collaborate, how do we build community, and how do we help folks learn the tools of data science that are so vital as we start to encounter larger data sets, we think about cross-disciplinary applications. And so I've been a little more in the space of supporting others in their research, and I want to share with you a little bit about what we've been learning in that work. So I am a data science fellow at a place called the eScience Institute, which is located on the 6th floor of the physics tower on the University of Washington campus. It's a beautiful space. If you ever get a chance to visit, we have great views of the mountains. And it's this open collaborative space where we're really helping to empower folks to use data science tools to answer fundamental questions in their research. So we serve folks all across the UW campus and beyond. And I think the ways in which this data science work really is infused into the work all of you are doing with iHARP is quite obvious to all of us. I mean, Arctic research will clearly benefit from harnessing data across multiple disciplines. Here's a picture of the Hubbard Glacier that I studied when I was up in Alaska. And during my early parts of my career, one thing that our glaciology communities learned is that the advance and retreat of these tidewater systems depends intimately on the temperature of the ocean waters in these fjords. And so when the oceanographers started sharing data with the glaciologists, we had this revolution in our field around how these glaciers fundamentally operate. One example of the many ways that this cross-disciplinary data sharing is so vital. We're now facing this situation where there's a deluge of data and tools to choose from. And so I think many of us are feeling overwhelmed by the different directions we can go in our research. And I think what we need is a shift in our culture to share towards sharing of data, sharing our code, and really focusing on inclusive community engagement so that everyone who has an interest in doing this work can take part, including those folks who are intimately engaged in living, near these glaciers in these communities that are most impacted by climate variability. So what I'd like to bring today is the things that we've been learning at eScience around open software design and how this can foster this sort of convergence and community that really relates to the overarching goals of iHARP as well. Now, I lead a program called the Hack Weeks, almost for the last decade or so. This is one of the core programs that our institute has designed that aims to bring these data science tools out into our communities. So Hack Weeks involve blending together the best of sort of a summer school tutorial type experience. Then these are tutorials that are designed by members of the community that are really responding in real time to the needs of researchers and the bottlenecks that they're facing in their work. And then ample time, usually in the afternoons, where people get together in small project teams and they learn by doing. Their hands on the computer, They're taking the things they learned in these tutorials and applying them to their research in real time. So these are very participant-driven events, and they're really infused with this notion of open source and open science. And we try to work with teams in a way that's very welcoming and a very collaborative space. So what I'd like to do is just share a story from one of the Hack Week streams that we've been involved with over the years as a way into sharing with you the concepts of open science and how it might apply to your Arctic research. So I'm going to take you on a bit of a story of one of the sort of success stories of our events in the past that came out of the ISAT-2 Hack Week that was initiated back in 2019. So we've now had 5 of these events. And our first event in 2019 was associated with the launch of the satellite. And this Hack Week model turned out, I think, to be a very powerful tool for something like a new NASA mission where we bring together communities into the same space, whether it's the DAC managers, the folks doing the research on the ground, the people designing the satellites and the algorithms, and then we can share our tools and codes together and lower the barrier to working with these data sets right from day one. One thing we noticed as we moved around the room is that every single participant at that event, there were about 65 people in the room, seemed to be using their own custom scripts and their different ways of gathering the ISAT-2 data. And so there wasn't even convergence around just the basic, getting our hands on the data. So a small project team formed around this idea of how can we harmonize all these different approaches, get everyone onto the same page and lower the barrier to working with the data. And we knew that it would be really important to include everyone at the table, including the DAC managers, in our case, the National Snow and Ice Data Center. So coming out of that project, the lead of that particular project is Dr. Jessica Scheik, who was a student at the time and is now a researcher at the University of New Hampshire. And Jessica helped to build a Python library that's now known as iCEPICS. So this is a custom community-designed library, open science library, that involves everything from data access to visualization, analysis, and cloud computing, focused primarily on the ISAT-2 data, but it's beginning to look at some other data products as well. And what we're able to do is take what used to be a couple hundred lines of code and reduce it to this, on the right here, a few lines of script level access to the ISAT-2 data products. And so Jessica now continues to lead this open source effort, and just a few weeks ago was awarded the prestigious AGU Open Science Award and will be honored at this year's event. And so what I'd like to do, well, here's just some of the outcomes of that kind of effort, just to show you what are the benefits of our communities coming together and building software together. Well, we have a whole list of, this is just a partial list of some of the publications. If you open up these papers, you'll see a reference to the iCEPICS library as being a core tool in the methods by which the data were accessed. And here's just one figure of many different products here. Bryony Freer's paper in 2023, looking at the grounding line of some of the ice shelves in Antarctica and using ISAT-2 data to assess, the grounding line locations. Also in the upper left, you see that iCEPICS is now listed as one of the core data access tools. If you go to the National Snow and Ice Data Center and click on the data discovery, you'll see this in the list. So all the different ways that this community-driven library becomes infused into our research data streams. So I want to ask, what were the conditions by which all these different successes were able to come together around open science? And I've distilled it down. So this on the left is just a partial image of all the different folks contributing to this work over the years and continuing to add their ideas to this work. And I'm going to divide this into 6 different categories. So it's things like the way in which these communities have been able to access educational training materials to contribute to open science, the way in which they've had opportunities for gathering as a community, the tools, the shared computational infrastructure for them to work together in these spaces, the way in which they adhere to these fairly strict software engineering principles so that we can build code really efficiently together. And then, of course, the funding and the supporting of the leaders and the people who actually keep driving this work forward. So to start with, and what I'm going to do as I share these different categories is also use this as an opportunity to tell you about what we at eScience think are some of the most, I guess, curated pathways by which you can, if you'd like to engage more in open science in your communities, some of the tools and pathways for that we would recommend, especially with the sort of focus on geoscientific applications. And I'll also mention from the start, which sort of alluded to earlier, we're going to focus today on the Python ecosystem and recognizing that there are many different ways to do open science, but most of certainly cryospheric and Arctic communities, many of us are working in the Python space, and it happens to be an area of sort of the greatest development around open science tools at the moment. So the Project Pythia is an NSF-funded effort to put together different trainings on the use of open source software in the geosciences. It's a fantastic set of tutorials. And it also has a series of use cases that you can access for things that may be similar to things you're working on. You can see examples of how to create scripts. So this is a fantastic online resource. For folks who'd like to learn some of the core tools of open science, the carpentries that have been around for quite some time. This is a nonprofit organization, just a fantastic volunteer-run effort. People sign up to be educators in the carpentries through a train the trainers process. And then different institutes will host virtual or in-person trainings where these volunteers are called upon. And then here's a picture of our institute offers several of these per year. And this is a place where you can spend a few days learning these core tools like GitHub and the basics of programming in these various different languages. So it's a fantastic resource, especially for those starting off on this journey of open science. Combining some of these online trainings with short format trainings as well, we can look to things like the great work that NASA Transformed Open Science is doing right now. NASA has really embraced the ideas of open science. There's the Year of Open Science as well that has been part of the federal government's recent initiative. So there are things like these self-paced virtual trainings, these massive online courses, and this is actually a requirement for NASA researchers now to be versed in these different tools. And then, of course, our Hack Weeks have these collections of online resources, and if you attend one of our events, can be a great way to learn these tools specific to your particular discipline, whether it's oceanography here or a specific mission like the SNOW-X mission, where you can if you're starting off working with SNOW-X data, you can turn to this as a starting point for accessing the data, processing some of the core tools, and really lowers the barrier to working in these communities. Other great resources out there include things like the Open SAR Lab at ASF. I know this is one of the institutes that was toured at the recent iHARP meeting up in Alaska. Great online resources as well as training opportunities to learn the tools to work with SAR data. And then I know that more and more these kinds of trainings are being offered in a traditional academic curriculum as well. When we started this work with our Hack Weeks and the short format trainings, there were very few, if any, data science programs at any universities. Now I know there are many being developed. This is just a short list of some of them, primarily at the University of Washington. And it's incredible that students who are in a traditional academic pathway can take an entire class now on things like geospatial data analysis using Python. So I expect that we'll continue to see more and more of these courses over time that will continue to expand the access to these kinds of resources. So as I go through these different categories too, I want to pause and think about some of the challenges associated with doing open science. Of course, open science is really bringing us a lot of new opportunities, but there are a lot of things that we need to continue being aware of and working on as a community. One of the things is the fact that there's so much content now, and there's a lot of overwhelm when you sit down to learn these tools, and especially if you're coming at this from, say, a mid-career perspective, you may not quite know where to begin. I know I faced that when I tried to learn some new tools myself. Accessibility can be a real challenge for the folks who may not have the resources to travel to a training. We know from the events we've offered that being in person is really leads to much greater positive outcomes when it comes to learning and developing new skills. And it's a little harder to do that in a virtual space. And yet we recognize that not everyone has the time or the funding to attend these events. So that's a real challenge that we face in bringing this work to more people. And then the short format training, the modality is a good one. And it has really been developed on the shoulders of a lot of volunteers over the years. And understandably, what that results in is a variability in the quality of the trainings. The fact that people are not always being compensated can lead to a variability in not really being sure if this is being backed up by things like pedagogical techniques that can help ensure that the trainings are done really effectively. So one of the things we've been trying to do in our work is to professionalize the short format training streams a little bit more, use things like evaluation, really rely on experts in adult education, things like that. I have a link here, and I'll share the link to all of my slides at the end. This link is to a fantastic paper about how can we professionalize the development of our short format trainings so that we can ensure that when people attend an event, they know they can be a little bit more sure about what they're going to be stepping into. Okay, moving on to the computational infrastructure. This is a really vital piece and has really revolutionized what we've been able to do in bringing open science to our communities. When we started this work 10 years ago, we spent the better part of the first couple of days of every event just scrambling to get everyone's local laptops installed with the right libraries and software. Now, if you show up to an event with a laptop that can access a web browser, and you have a GitHub account, you can access these amazing resources through things like Jupyter Hub, which is a distributed computing platform for getting folks into a shared computing environment where they can run Jupyter books. I'm sure many folks are aware of these great interactive tools for building code together. We partner, in our case, with a group called CryoCloud, and they are an organization that has their deployment of Jupyter Hubs available for us to use in trainings, and as well as for other collaborative work outside of the week-long training events. They contract all their networking and development of the hubs to a nonprofit group called 2I2C. So we're moving away from all of us as researchers having to be system administrators and partnering with groups who can design these tools that can support our research infrastructure. Many of you, I'm sure, are aware of the commercial options for looking at earth science data. All the three main providers, Google, AWS, and Microsoft, have earth science focused data repositories. Of course, Google Earth Engine also has a computational environment for using JavaScript or Python to process data, so we can come in and look at the entire Landsat stack, for instance, and do this high performance sort of multi-data set computational work. And this has been a great tool for many research applications. So again, some of the challenges associated with this, working in the cloud and in some of these shared computational environments can be costly, and it can be difficult sometimes to figure out if you're deploying instances, say on AWS, to navigate that on your own as a researcher can be challenging, although there are some efforts to really streamline that. Some universities have struggled figuring out overhead rates and how that applies to cloud computing. And then if you're not savvy with some of the tools and they are changing rapidly, it can be easy to accidentally deploy say a large CPU instance and wake up the next morning and see a large charge on your AWS cost mapper. So these are some of the things that folks in research have been struggling with a little bit with cloud computing. When it comes to, say, running large computational models or machine learning workflows where we need access to graphical processing units or GPUs, what I just showed you with the Jupyter Hub is not a great solution for that. It's not a high performance computing environment. It's more of a shared analysis space and a learning space. So this is an area of growth for us still in figuring out how do we provision HPC resources to folks who need them Typically, that's done through federal centers. So if you have an NSF award, you get a certain amount of time on an HPC, or you may have your own local resources at your university. But this is still an area of challenge for a lot of folks. And then a last one here is when it comes to, and I noticed a bit of this cropping up at the iHARP meeting as well, and I've dealt with it in large teams that I've been on in the past. How do we share large data sets internally? If I have a collaborator on a large team like iHARP who's created a model run, and I'd like to look at that and do some collaborative work, that remains a pretty big challenge. I want to dive into that point here with just a little concrete example from work that I did back in a project that I was engaged in with High Mountain Asia work associated with a NASA project. So I was involved with looking at some gravity recovery and climate experiment data, and I was trying to collate that or connect it to some of the 1 kilometer resolution land information system data sets. So these LIST model outputs were distributed in netcdf files, daily files. And I wanted to show you a little workflow that we developed just to exemplify what kind of a modern data science approach would be to this particular problem and how we could leverage that going forward. There's a new data format that's being used in cloud optimized workflows now called ZAR. And so what it does is it chunks the data down into these smaller sizes in a format that's different from these daily netcdf files. And with the data in that chunked format, it can then be fed into these other workflows that are described in this graphic here. So you can imagine the data coming in on the left-hand side, and that can be read into a library called Dask, which is a Python library that's a task scheduler for parallel computing workflows. And sitting on top of that is another library called Xarray, which is a multidimensional labeled array toolkit. And with that configuration in the cloud or on an HPC system, we can vastly minimize the effort that goes with processing these rather large outputs. And I'll show you just a little screen capture here of a notebook that would take this high resolution data and allow us with some fairly simple lines of code using Xarray and Dask within a web browser to then run these computations. And on the right-hand side here, you'll see the task stream spinning up. And what this is doing is distributing each of those small chunks of data across multiple processors and multiple cores. And it really enables us to do this very high resolution, rapid aggregation of data using some of these modern data science tools. This is something we worked on, I can't remember, 8 years ago or so. And these kinds of cloud optimized approaches still haven't really made their way into standard workflows. And there are a number of barriers to us doing that. One of which is just, actually natively hosting the data in these cloud optimized formats would be a real step forward that would allow us to use some of these tools. But it takes time to kind of shift our toolkits in those directions. So the next category it's an area that I'm working more on in the last year or so is what can we learn from the principles of software engineering and professional software design when it comes to how we do our science. And so, it strikes me that we have fairly strict norms and patterns of how we work together as scientists when it comes to publishing our research, whether it's the way how we structure our papers and share data with each other. And at eScience, we're really advocating for how do we apply similar norms to our research software work, and what can we learn from the professional software engineering groups who do this work all the time. So specifically what this means is increasing the quality of our code around things like documentation, making it easier for people to know what our code is actually doing and ensure that it's reproducible. Things like testing our codes, actually writing scripts that will ensure every time that we make a new update, the code integrity is maintained, and we're checking for physical constraints as well. Packaging, so how do when I'm ready to share my code with someone else, have it so that they can install it off of an online repository rather than emailing or even downloading from GitHub. They can actually just install it as a Python library. and peer review, so formal paper-based processes or a process by which, in a similar fashion to a research paper, our code gets reviewed and other people look at it following these standards. So two resources I would point you to there that are really fantastic. On the left is a group called the Scientific Python Development, or Scientific Python group, who've built a development guide they provide templates for how to set up your different workflows and repositories to adhere to these principles. And then PyOpenSci is a great organization, volunteer run, and they have a number of different educational activities, and one of their core offerings is how do you follow these best practices around code development, documentation, licensing. So really great step-by-step way to work in this kind of fashion. So applying these principles to your work, of course, is going to have a number of challenges. It takes a lot more time to build our code in this fashion. It's going to add considerable effort. And if you're a graduate student trying to graduate and finish your PhD, you may not have time to package up your code in this way. Not to mention, of course, anyone else at any different career stage. I was chatting with a colleague who's worked a lot in industry the other day and was really struck by just how differently we approach our work. So someone in industry will probably have a core goal that's already set out in the team, and they're going to use design thinking around how they build their software to get to that goal. Whereas as scientists, we're often in more of an exploratory space. So we're kind of having to write code and then maybe after the fact go back and refactor it and clean it up and adhere to these principles. So our basic approach can be a lot different. And in terms of learning these tools, it still hasn't really infused into academic practices. And when we look at the industry side, a lot of times there'll be a more senior mentor in the group who kind of exemplifies these practices. But in academia, it's often, younger folks who are learning these things because it's becoming a little bit more of a practice. And it's just a little bit harder to kind of infuse this across the entire culture of our work. One of the things that's really interesting at eScience that's occurred in the last couple of years, and is a resource for all of us to think about, invite you to have a look at the website here. There was some funding from the Schmidt Futures Foundation, and it was really focused on how do we save neglected scientific software. In other words, if you are a researcher who has a system of code that you'd like to tidy up according to the things I've been talking about, you can apply to this group and through a proposal process, get a chance to work for a couple of months with one of these amazing research software engineers. So these are people who have expertise both as professional software designers, often coming from an industry background, and also have a really strong footing in research. And so it's kind of a new career pathway blending those two worlds. And what we're seeing is great opportunities for people to develop their code, package it up, and hopefully be mentored along the way and bring some of these practices back to their communities. The next category is regular gatherings as a community. What we know in this work is that open science really can thrive when, and really requires a lot of detailed communication, sharing of ideas, open questions and answers across the community, because a lot of this stuff is very new as well, and it's hard to always navigate pathways through it all. So here's an NSF NASA funded effort called Pangeo. It's been around for, I think, about 10 years now. It's primarily now community for a public discourse around these different tools. A great resource for you to check out around open science and geoscience applications. I'm really impressed hearing about the immersion days that iHARP engaged in with their industry partners at AWS. I'd like to learn more about that. And then, of course, our Hack Weeks are great opportunities, and there's many other, I know, workshops and community gatherings. So another quick plug for what we're doing, just to let you know that if anyone is interested in running their own Hack Week, you can visit our website. We have been developing our events into kind of a Hack Week as a service type model. So community members coming to us with a need, and we provide the infrastructure and the scaffolding, the tools, and then help support you in designing one of these events. So feel free to reach out if you have interest in that. This one is the fifth category, and it's around really empowering and supporting leaders. What we notice in open science is, even though we talk about it being this huge community grassroots effort, often it's the work of one or two key individuals. In the case of the story I told you, Jessica Scheich, doing a lot of the groundwork around the development of this library. And so I think a really great model for how we amplify this work is focusing in initially on these leaders who have a lot of energy and engagement, and we see how we as a community can help amplify that. And I'm highlighting here the fantastic work of a group called OpenScapes, Julie Lowndes and others, who have worked with a number of different communities over the years, and this is one of their sort of conceptual models, this idea of a flywheel. It's like bringing folks into a community, mentoring them, providing training, and then they go off to their own lab and they spread these ideas, and we have this virtuous cycle that grows over time. I've been learning about things like your SIG Spatial Cup, which seems to have some of the same elements of working with young students, helping to amplify what they're doing, and they hopefully then continue to spread the word. So these are just, I think, some of the core tools by which we can shift our culture towards inclusive engagement, empowering young people, typically early career folks and researchers, to then bring that back to their own communities and continue to move this work forward. There's the importance of having funding to keep this work alive, and I know there are obviously many different pathways for this. These are just some that I'm aware of right now. NOAA Fisheries is investing a lot recently in advancing and modernizing their data infrastructure, and including funds to support, actually OpenScapes is one of their contractors for this work that they're supporting, and other trainings and open science work. So this is part of the recent Biden-Harris workforce development. NSF has had a number of great programs over the years. The Pathways to Enable Open Source Ecosystems, more around kind of the infrastructure of open source communities, and then the Advanced Cyber Infrastructure training-based workforce development. We've had funding from that funding stream to support some of the trainings we've done around machine learning and the geosciences. Then there are a number of opportunities within NASA funding through TOPS and through enhancements to your existing awards to build out an open science component and a software development piece to what you're doing. Okay, so I'd like to finish today with just two more slides to highlight a couple of other areas of activity and resources that I'm aware of, that I learned a bit through preparing this talk, and I'm sure there's many more, but I just wanted to shine a light on a few additional things. The first is these incredible open source tools in the glaciology community. The Open Global Glacier model, not only a collection of open source software to run models and analysis, but also a fantastic collection of educational tools and resources and community gatherings. Of course, the parallel ice sheet model that is being led by members of the iHARP community. It has been an open source ice sheet model right from its inception, and is a fantastic shared tool for doing ice sheet modeling. GHub, which I'm learning a little bit more about as a hub for connecting with HBC resources, code sharing, and community development. And then I'm just becoming aware of things like the Open Storage Network. So this is an NSF-funded effort. And I think what it aims to do is address that issue I referred to earlier around the sharing of data across institutes, where they're developing methods by which different universities can connect different pods of data and sort of overcome some of those challenges of connecting data sets across institutions. And then the Science Gateways Community Institute, also NSF funded, and I believe this is working kind of in that space of the research software engineers that I refer to at eScience, where folks can come in researchers can partner and get consultation and education on things like website development, sharing of data sets, all the different technical tools through this community institute to help create solutions for their research needs and accelerate their research discovery. And then I'd like to finish by just speaking to the incredible work of navigating the new Arctic, the open science piece, which is one of their 4 core activities, and learning about the importance of applying fair and care principles and thinking about this open science story from an Indigenous data perspective is so important. I've not had the opportunity to work a lot with Indigenous communities, but I'm really beginning to learn more about how important it is to honor the sovereignty of Indigenous data, and thinking about what we've been talking about today. How do we curate and protect and treat Indigenous data in a very culturally sensitive manner through the tools and the approaches of open science, making sure that we really partner with and include Indigenous communities in all the phases of our work, from the beginning of data collection all through the entire data lifecycle, and relying on our community partners to decide on if and when data sets that are collected by Indigenous communities will be shared more broadly. And I think we have this assumption in open science that everything ought to be shared openly right away. And the importance of recognizing some of the harms that have been incurred on Indigenous communities through Western colonial scientific practices, and that it's important to be sensitive to those past injustices and really be aware of honoring the sovereignty of these data sets and including everyone at the table. So really appreciate the work of this community, and I think needs to be infused in how we think about this going forward. So I appreciate your attention today. I'm happy to have any additional discussion in the time we have left. These are some of the links to contact us. And yeah, thank you for welcoming me to this talk. And I'll leave it there. Thank you.
Thank you so much, Dr. Arendt. This has been a very insightful talk. Do we have any questions from the audience? We have 20 minutes. So Dr. Wang, please.
Yeah, Anthony, thanks a lot for the very resourceful talk. I think it did a lot of information, not just your own work, but also other resources useful for this polling informatics field. I have 2 questions. First is that you talk about this library you work with as IDC. They're able to host the software, not host, but actually list that as one of the core way to access their data. So I wonder, how did you contact with us at IDC? How do they need to make any changes to their infrastructure to be able to work efficiently with your toolkit? How long this process take, and how much effort you need to do to convince them there's something useful. It should be a win-win situation where users will benefit from it. Also, as a data provider, as you say, they at least they don't that's something they don't have to do too much work to host your toolkit. Second one is about the cloud computing credit. You mentioned about overhead. For example, at your university, if you have a proposal using cloud computing, do they still charge overhead for it? Like, do you have a way to negotiate with your university to have a no overhead for the cloud computing credits, the cost? Because I think that's a common issue for many universities right now.
Thank you. Thank you for those questions. They're both great questions. So the first one, asking about how did we include NSIDC, one of the DACs, in the development of our software, the IcePix package. And it was so important for us to include DAC technicians and managers. They actually attended that first Hack Week. We reached out to them, and they've always been very open to partnering with us. So we had existing relationships, and then we had them in the room when this work was started, and they became some of the core contributors. They were always open to consulting with us around their so-called common metadata repository, and they were open to modernization of what they were doing. So it really depends on the group that you're working with, but in our particular case, I think because we had this open relationship to begin with, that created the conditions for us to partner. And it was, I think they realized that it was to their benefit to have this community effort to maybe minimize some of the work that they had to do. So it was a very positive partnership and a great example of how a community coming together can help exemplify like, what are our needs so that you as a data center can help us meet those needs. Sometimes I noticed earlier in my career there was a disconnect there. Engineers at a data center would go off and create a bunch of tools, and then we'd go to use them and they weren't quite matching what we needed. So I'm really glad to see this shift in our culture. And then the second question is related to overhead of cloud computing resources. It's been a little while since I've deployed that for myself. I'll mention a couple things. One is, at least at our institute, there was a recognition that cloud computing at the commercial providers was kind of in the category of a core institutional research need. And so we were able to, at UW, waive the overhead eventually. There was some confusion over that in the early days, but it's now being waived. I'll mention that Cloud Bank, an NSF-funded effort to help navigate some of these issues, is a great resource to check out, and I think they can provide more clarity on that. I think it still is kind of institutionally determined, but my understanding is many institutions are kind of moving away from charging overhead on that. I can consult with some of my colleagues who know a little bit more about that, though I'm not 100% sure.
Thank you.
Thanks.
Dr. Sherman, please. We'll have Dr. Sherman, then Maria here.
Hey, Anthony.
Hey, Chris.
Good to see you again.
Good to see you.
And you've obviously been keeping busy. One of the things which we're hearing more than we'd like to locally here in Greenbelt is kind of budget uncertainty. And so I guess I'll make it kind of a broad question just to give you plenty of space to roam in. But DACs are not cheap. What sort of financial vulnerabilities are these efforts subject to going forward, given that we are again on a continuing resolution? Cheers.
Yeah, Chris, say a little more. Like, do you mean things like, say, the Jupyter Hub I was describing, or just the DAX distribution of data in general? Help me narrow in on that a bit.
You can focus on what you're comfortable with, but there's this feeling that what used to be a kind of given for researchers coming along may be less certain in the years to come. I apologize that is rather broad, but it is.
No, that's fine.
It's something we're all sort of worried about in the back of our minds these days.
Yeah, I hear that. I can say a few things. I mean, I do think so. When I was mentioning CryoCloud, there was some brilliance to the design of that because it's this grassroots effort, and it allows researchers to contribute funds into the larger pot of money that goes to deploy those resources kind of as they have funds available. And the folks leading that effort have been able to keep it alive through that model in a very sort of distributed grassroots way that is kind of an interesting new approach from the more top-down institutional DAC model. So I'm saying that in the sense of that gives me hope that some of these community-driven approaches just might innovate around new ways of doing things that help us solve those challenges and make the most of existing resources. When I look at things like NISAR coming online, where the data volumes are just so massive, I can see that urgency and that scrambling to kind of figure out how everyone's going to navigate this. And again, I think the fact that groups like the Alaska Satellite Facility are leaning on community open science efforts to help figure that out together gives me a lot of hope, I guess. And I think that together we'll find solutions despite some of the tightening of budgets. But I hear that, like even thinking about some of the commercial providers, you never know when they'll start charging for that free Landsat stack of data, and there's a lot of volatility there. So I think, yeah, I think it's just a constantly shifting landscape, and we have to just figure it out as we go along.
Sure. Keep the ultimate goal in mind, but be prepared for changes ahead. And I'll mention that the USGS is already beginning to work on collection 3 for all the Landsat data, and this is not that many years after collection 2 was rolled out, and there were some consequences to slight changes in the data between collection 1 and collection 2. So there's that need to be nimble for everybody involved.
I guess I'm also thinking that the better we get as a community at figuring out, efficient data storage methods and not replicating the same data files across multiple DACs or multiple servers, then that's going to maybe free up space. We can do things more efficiently as a community when we adopt maybe more of these open science practices. I'm not trying to be, Pollyannish about it, or that this open science solves everything, but I do see so much innovation happening at that level that it gives me some hope that solutions are out there to some of these challenges.
Okay, great.
Yeah.
Let's hear it for hope. Thanks.
Yeah, thanks, Chris.
Maria?
Yes, I can't, for some reason, my camera is not enabled, but I just put 2 resources. I wanted to clarify that any researcher in this country, even if they don't have an NSF grant, they can access supercomputers and cloud computers through Access, and I put the link there. And I know because I work at the Texas Advanced Computing Center and we participate from that network of computational resources. And I also put another Jetstream, which is cloud computing. So you don't need to pay. It's free, and you don't have to have an NSF grant to access. And there's plenty of resources and tutorials, etc. So I encourage people to look at that because that's really open science and free, and it may take a little bit more of time and effort to learn how to use these resources than AWS and Microsoft, etc. But it is affordable. I mean, it's free, and it's what the government or taxpayers we pay in order to provide these resources. And that's all I wanted to say. And
Thanks so much, Maria.
It also includes large-scale storage, which means that you can have your data close to your computation, and that is just what you were talking about. So you don't need to,
Okay.
That's all. Thank you.
I really appreciate you sharing those. Those are new to me, and I'm going to add them to my deck of information. So thanks so much for adding that piece. I didn't know about those resources.
Thank you, Maria. So I don't know if anyone has questions, but I can share mine right now. So you have shared a number of tools. Your research background is in, the polar science, Arctic. But how would you advise a group like iHARP? What tools should we focus on? When you attended the All Hands, it's so a diverse, group of research that is being conducted at iHARP. What would be the best tools that could target?
That's such a great question. Thinking about it, I might begin by assessing kind of where are people starting from? What are the tools that they currently use? Is it, is everyone primarily working in MATLAB or in Python, or what's the distribution, just so we can get a lay of the land? And then through some kind of survey evaluation process, just seeing kind of where are the bottlenecks. I got a little flavor of that when I was there. I wasn't able to immerse in all the different connections, but my understanding was there are some bottlenecks around, similar to what I was describing with respect to sharing data across teams. And so, getting folks onto some kind of shared computing resource, kind of like what Maria was just describing. And I think a big part of this is helping folks talk the same language. You know, I see this a lot when data scientists, more pure computational folks, get in the room with domain scientists. And so I think finding ways to bring people together in workshop settings just to help lower that communication challenge is a really big piece to moving this forward. And then again, that model of, you know, finding those small handful, often it's younger researchers who just have a lot of energy and they're really understanding some of they're really skilled with a lot of the modern tools of data science. And so then empowering them, funding them, giving them time to kind of spin up this work and create tools that meet the needs of the broader team can be a really powerful approach, I think. Those are some key areas where I would spend some time.
Thank you so much. Any other questions from the audience? So Dr. Arendt also serves on our PHICC, so his contact information is available there if anyone wants to follow up. But we do have a couple of minutes, so if anyone has a question or comment, please feel free. I want to maximize all this time with him.
Can also give folks a few minutes back if they want.
I think if no one asks, I wonder what's your suggestion to the students? I think many of the audience are students. I think they are facing the dilemma how much they should spend time making their software more usable by others, or spend the time doing more research and read a paper. What was your suggestion to the next generation of a researcher?
Yeah, we have conversations about this at many of our events, and I hear a lot of concern about that and people wrestling with that very question. I don't know I'd be curious to hear what you're seeing, Dr. Wang. What do you notice?
I know that it's struggling. I think it's a new challenge to them. One thing, if you have a good toolkit that actually have many people using, is a big community impact. Right? I think like people saying how many stars their GitHub repository has, and like that can be part of their resume, saying how many people actually utilizing their tools software. But at the same time, you know, you might need to spend a lot of time even just documenting how to use it, how to people other people to install it. I don't and you know this scientific software developer is a new profession. Not many people taking this route. They might still want to the faculty or go to industry as their first choice. I think somehow they are based on the current pressure or requirement, they spend more time on the paper, on the research, not on software.
Yeah.
Maybe, for example, the journals that have those open source software, they have more impact that maybe give the community more focus to spend more effort on those things. But I think that now it's definitely a community issue. It's not like one person can solve it.
Okay. Yeah, I think it depends a little bit on if you have a sense of what your trajectory is. If I was quite clear that I wanted to be a researcher throughout my career, then I would see that time investment as being worthwhile because it would build a foundation of work that I would go back to for myself. And, you know, I think just in terms of the integrity of our research, moving in this direction to make our work reproducible, I guess I'll say I regret that I didn't have the tooling or the time to do that for many of my earlier papers. And, you know, in a sense, that work certainly can't be resurrected, or it was a different time back then. So I think it's from a perspective of the integrity of how we do our science, it really matters. And then we have to balance that against the practicalities of finishing a degree and if you're more in the direction of, wanting to work in industry, well, I guess even there, you're going to develop a lot of great skills as a data scientist that have transference to other career pathways too. So I think it's a win all around, but I think depends then on, whether your supervisor and the folks around you recognize that as valid academic output or not. And I think the culture there is changing too, but not everywhere. So yeah, a lot of complexity, but I hope
Yeah,
people
I think I totally agree. I think the younger generation, I think the culture is shifting. We traditionally even for faculty to be successful, the most talking about their papers. Now they can talk about papers and the impact. How many people are using their software. Like we were talking about Open Science Award to the person, and in industry and the research scientific software developer. Those are also careers that need a lot of software development skills. I think those things. I think all around people rely on notice this importance of it, and the culture shifting toward it. It's not that much like the tenure case. They still look at most on research, not too much on the software. But I think it is shifting to that direction, to the right direction.
Yeah.
Thank you so much. We'll definitely follow up with several questions. I know on my end, for sure, you're going to hear a lot from me.
Oh, yeah.
We have recently got a new project for Open Science, so that is going to be directed towards those efforts. So you'll be hearing a lot from me. Yeah.
Oh, yeah, that'd be great.
So thank you so much again. And if anyone doesn't have any questions, I would love to let Dr. Arendt get back a few minutes of his day. And we wish you all the best, and we appreciate your time again.
Thanks so much. I really appreciated this opportunity.
Okay. All right.
Take care.
Have a good one. All right. You too. Bye-bye.
Bye-bye.